All right. Good afternoon and welcome to the Transportation Infrastructure Durability Center's June webinar on dynamic remote sensing and optical distributed sensing applications for bridge health monitoring. My name is Aaron Schanck, Communications Specialist for the TIDC, and I will be moderating today's event. The Transportation Infrastructure Durability Center is the 2018 U.S. DOT Region 1 University Transportation Center located at the University of Maine Advanced Structures and Composites Center. TIDC's focus is on extending the life and improving the durability of transportation assets through 4 research thrusts: advanced structural and performance assessment, development and implementation of novel materials, advanced structural systems and applications, and enhanced performance through innovations in safety, resilience, and connectivity. TIDC has 6 member universities within the New England region: the University of Maine, the University of Connecticut, the University of Vermont, the University of Massachusetts at Lowell, Western New England University, and the University of Rhode Island. Today's webinar will consist of 2 20-minute presentations followed by a live Q&A session. During the presentations, please use Zoom's Q&A feature for any questions you have for our presenters, and we will go down the list during the Q&A session. If we don't get through them all during the scheduled time, there will be a link at the end of the webinar to submit any further questions, and we'll email you a follow-up to that. Our first presenter today will be Dr. Tzuyang of UMass Lowell. Dr. Yu received his PhD from MIT in the field of structural engineering and materials, specializing in the remote electromagnetic imaging of concrete structures. He is a recipient of the 2008 ASNT Fellowship Award, the 2010 Fellow of the JSPS, 2021 ASNT Faculty Award, and 2022 Acorn Innovation Award. He also received the 2017 Donald Leach Award from the CEE department at UML for outstanding research performance. His research has been sponsored by NIST, AFRL, NSF, DOE, USDOT, UMass SNT Office, AFFOA, and NextFlex. Our second presenter today will be Dr. Xingwei Wang, also of UMass Lowell. Xingwei Vivian Wang received her PhD degree in electrical engineering from Virginia Tech in 2006. Then she joined UMass Lowell as an assistant professor in 2006. She was promoted to associate professor in 2012 and then to a full professor in 2016. She is the recipient of the 2010 NSF Career Award and the 2008 Massachusetts Life Science Center New Investigator Research Award. Her research interests include optical biosensing and biomedical devices, optical sensors, optical imaging, MEMS technology, and electromagnetic wave propagation. She has published over 80 papers in journals and conference proceedings on design, fabrication, and the characterization of optical sensors and devices. For the Q&A session, they will be joined by industry partners Elvis Higgins, Technical Director of Engineering Innovation at CSX Transportation, and Matthew Davis, Regional Sales Manager at Luna Innovations. So, without further ado, I will let Tzuyang share his presentation.
Thank you very much, Aaron, for the kind introduction. Good afternoon. I'm a faculty member at UMass Lowell in civil engineering. And today we would like to present our research results on 2 different kinds of sensing technologies for bridge health monitoring. Joining me today is my colleague, Professor Xingwei Wang.
Hi, everyone.
And we will be talking about the first dynamic remote sensing application for the steel railroad bridge, and the other technique is the optical distributed sensing for a composite bridge. The presentation will be structured by giving the audience an introduction on the backgrounds of remote sensing and optical distributed sensing. And soon we are going to introduce our research results and showing what we have done in the field to demonstrate the applicability of these bridge sensing technologies for practical solutions. And then we're going to conclude our talk by summarizing major findings. After that, there will be a Q&A session. Starting with the overview of the U.S. infrastructure, as we know that the US has a large and growing aging civil infrastructure population. Ideally, when we design the infrastructure system, it could be bridges, could be pipelines or airports, all different kind of infrastructure systems. The condition of this infrastructure was supposed to degrade initially at a slower slope. And over time, we know that they're going to gradually degrade to the terminal level. Before the terminal level, a decision must be made, whether a reconstruction is needed or a repair must be done. Under no circumstances, this infrastructure system should fail in a surprise. Nonetheless, pictures show on the slide that in 2005, this Lakeview Bridge actually collapsed unexpectedly. So that means we could do the better job with the infrastructure sensing, because as a researcher and also for the stakeholders, the condition of our civil infrastructure was not properly controlled or aware by our stakeholders. Therefore, bridge health monitoring is a very powerful and beneficial techniques that can help these governments to reduce the risk of these kind of certain failures, as well as to help structural engineers to improve their design knowledge. Showing here are just a number of applications that we can learn by using bridge health monitoring. And among them, predictive modeling is what we focus our research on, because the purpose of health monitoring is to be able to predict the condition of the bridge in the future. Therefore, having a time-dependent model regarding the structural properties of the bridge is essential to the success and the value of bridge health monitoring. Now, in the big picture, this information can help the stakeholders in achieving a more efficient and better asset management. Bridge health monitoring is one type of a structural health monitoring. So if you look at the components of a structural health monitoring systems, all these components still apply to bridge health monitoring. There's the data acquisition. Today we use remote sensing or smart sensors to collect the response from the structure. And there must be a power supply component. The data transmission could be wireless or through wired approach. And there's the data storage, processing, mining, and interpretation. With the advancements of different technologies, digital twin has gradually evolved into the two components for structural health monitoring. Very soon that we can expect that all these infrastructure systems should have a digital version such that engineers can have a better idea about what is going on these bridges. Another overview about the existing remote sensing technologies. There are many different classifications of remote sensing technologies. And in our perspective, if we can categorize them into a portable and a mobile one. So what's the difference? The portable ones means that the sensors are under strong human supervision. The mobile ones means that the sensors are conducted or collecting data under indirect human supervision. The portable supervision means that the inspectors will have its flexibility to decide and refine the measurements because the decision was made at the time was inspection. But the mobile inspection using drones or using other type of moving platforms will require the pre-designed inspection route in order for the inspection to be finished within a given amount of time and with expected resolution. Now, showing here are two different examples. One is the use of infrared thermography, and the other one is a laser Doppler vibrometer. Thermal infrared thermography is a good example to show how we can use remote sensing to obtain high-resolution surface condition. But a laser Doppler vibrometer actually can give us a little bit in-depth understanding on the structural properties, because the surface information must be correlated to the subsurface condition in order to understand how a structure age. Now, another big picture that we can see here is the growing potential of unmanned airborne vehicles or unmanned airborne systems, UAV or UAS. They can actually carry different type of sensors and to collect data and to save inspectors' time and reduce the safety concerns. When it applies to bridge health monitoring, remote sensing technologies also have been widely applied to different kind of components and also different parts of a bridge. What we can see here is that if you use a ground-based systems and the more detailed inspection for subsurface condition inspection have already been applied. But if you fly the small UAS, you can actually use the LiDAR or GPR to collect or to generate the digital version and to have the radar-based image of the entire structure. To inspect the bridge piers or the subsurface underwater foundations and underwater unmanned water vehicle systems will be required. Of course, to improve the inspection efficiency, airborne systems was actually the first applied in the bridge health monitoring. Now, if we look at these existing technologies, they are essentially using two different types of waves. They are either mechanical waves or electromagnetic waves. For mechanical waves, the most popular approach are acoustic emissions and ultrasonic testings. They are basically using the vibrations and transmissions of mechanical waves. And through measuring this surface mechanical response, we correlate this response to the presence of subsurface or surface defects on the bridge. But electromagnetic waves can be used to obtain the subsurface condition of concrete structures. Now, among these different methods, either mechanical or electromagnetic, we can even see them as either actively probing into the bridge or passively collecting the response of a bridge under, for example, traffic excitation. So showing this picture, this slide here is just to prepare the audience to have a more broad understanding on the diversity in existing remote sensing technologies for bridge health monitoring. Now, in this talk, our focus is on the use of laser Doppler vibrometer. Now, the principles of a laser, for those who have not or do not have much experience with a laser, essentially it's by exciting an elements from the ground state to the excited state. And depending on the type of elements, when this excited state is gradually reduced to the ground state, different types of electrons or photons will be released. Now, by generating this resonant response of these photons or electrons, a laser beam will be generated. The fundamental principle of laser Doppler vibrometry is based on what we call the Doppler shift effect. The Doppler shift effect is a well-known effect that many of us have learned this even as early as in high schools. So when the object is moving toward the laser, then the frequency will be increased, the wavelengths will be reduced. And this is what we call the blue shift. And the opposite of the blue shift is a red shift. So from this Doppler shift effect, we can easily correlate the frequency change to the velocity of the object. Therefore, in the LDV, the direct measurement is the velocity. If we can continuously collecting the velocity over time, we can generate a velocity time graph. And by integrating this velocity time graph, we can obtain the displacement response. Or if you differentiate the velocity time graph, you can get an acceleration time response. And the system we use in this particular application is a commercial unit. It uses the short wavelength infrared, which means that the laser beam was not visible to human eyes. However, we equipped this LDV with a visible laser. Therefore, when we deploy it in the system, there will be a visible green spot to help the inspectors to detect or identify the location of the inspection in the field. This system is ideal for far field measurements. So our application is well within the range for this particular LDV. The bridge we selected for demonstrating our health monitoring technique, it was one at the border of New Hampshire and Maine. It's a Salmon Fall River Bridge. and it has the main span about 65 feet. But the age was actually uncertain. The next slide will explain why. It's basically a steel girder bridge, and the foundation was mostly masonry and perhaps partially concrete. And the reason why we said that the age was uncertain was because at the time when we performed the health monitoring, we look into the records of this bridge. We found out that even so that from some of the bridge records, it shows that this bridge was built in around at the turn of the 20th centuries. However, there's a map actually showing that the bridge was there since 1877. So we believe that the foundation was older than 1877, but the superstructure was rebuilt perhaps around 1912 or 1920s. So that gives us some idea about how old this bridge was. A major reason for choosing this particular bridge for health monitoring was because of its convenience to perform this kind of under-bridge inspection. Because this bridge was located at the junction of two major roads, but there's another road passing by this bridge, such that most of the traffic will not be going through this particular, going underneath this bridge. There's only a recreational park that connects to this road. So that gives us a lot of flexibilities in data collection. Because of that, we choose the midspan and position our LDV at 90 degrees, such that we can measure the direct and perpendicular measurements at the midspan. On the slide, you can also see the green spot showing the location of this LDV beam. So let's take a look at what the raw data look like. First of all, we have the velocity and time response. And what we must do as a first step is to understand the background vibration signal. And this was achieved by integrating the velocity time response into the time domain. But this integration is associated with a well-known problem, which we call the rigid body motion. When you integrate the velocity into the displacement, you can see the drifting of the displacement response. So this is the rigid body motion. And in the frequency domain, it is manifested by a large zero frequency component. And this zero frequency component is not a real signal, so it must be ignored or even removed before we proceed with further signal processing. But from the signal processing or the frequency response of the displacement, we can see that there's a major frequency component at 55.67 Hertz. And this frequency component was the vortex-induced vibration from the river. In order to extract the dynamic properties of the bridge, we rely on the traffic-induced vibration. In this case, there is an Amtrak Downeaster train that has 6 to 7 train schedules every day. So we were there and waited to capture the loaded and the force response of the steel bridge due to this Amtrak Downeaster train. And from the information on the MBTA, we found out that this train model and also the passenger train model. So the dimensions of the locomotives and the passenger trains can be found. Now, by taking a look at the total response, converting the velocity time response to the displacement time response, our second step is to use the displacement time response to separate the force response from the free vibration. And then we process the force response to get some parameters that we move to the free vibration response. Showing here are the time domain and the frequency domain curves of the velocity response and the displacement response. Now, interesting thing about this response was when we take a look at the force response and the free vibration response, this is the result we got. And at the time when we collect the force response due to this locomotive train, we saw there are 2 locomotives. But in the displacement response, we only have 4 peaks. The reason why I call this interesting was at the time when we collect this when we measure the dynamic displacement response using the LDV, they were actually 5 passenger trains. So it was puzzling to us that why the 5 passenger trains only resulted in 4 peaks when the 2 locomotives generated 2 distinguished peaks, as we clearly see here. The reason is what we call the dynamic hysteresis response. That's because when the heavy load is moving, in this case, is a heavy load but with a distributed axial loads, the center of gravity actually was slowly shifted toward the second part of, or toward the end of a distributed load. Therefore, while we can see there are 4 peaks representing the passenger trains, but these peaks are not at the center of these passenger trains. They were actually at the joints of 2 passenger trains. Hence the 4 peaks for 5 passenger trains. Now, when we use this response, we have to use the displacement measurement in order to calculate stiffness. Therefore, we actually need to use the displacement values at individual axial loads and use these axial loads to calculate the stiffness of the bridge. For structural engineers, this could be some tedious work because every individual load is not created by a single axial load. It was actually the combined effect of whatever axial loads were on the bridge at the time. So to do that, we will need to know the dimensions very precisely and very accurately. And for train loadings, this was actually possible because we have the dimensions of these trains. So the first thing we did before we calculated mass, damping, and stiffness was to estimate the velocity because the measurement was in time domain. And if we know the distance between any axles, then you can use the displacement, you can use the peak-to-peak distance and also the time information to calculate the average velocity. So the first over global information we obtained was actually the velocity of the train. And in this case, the average velocity of the train was about 56 miles per hour. And the limit was 73 miles per hour. So at least we knew that this train did not speed at the time. Now the next step is to separate the force response from the free vibration. So because we want to use the free vibration to get some parameters. And this separation has to be done with care because the end of the force vibration and the beginning of the free vibration sometimes will overlap. And if we accidentally include the wrong components from the force vibration into the free vibration, your spectrum response in the free vibration could be misleading. So we use the frequency domain method to separate the force response from the free vibration response. By doing so, we get the spectrum response of the free vibration. Now, once we have this step, we also have to make sure that we can only use a single mode vibration to calculate the damping, because the attenuation curve that we are looking at here on the slide actually contains multiple modes. If in the free vibration, there are multiple modes present, and this attenuation curve cannot be used to calculate the damping ratio, as we know that from structural dynamics. Therefore, the next step is to remove the influence of all other modes by keeping whatever the desired modes present and then convert it back to the time domain. In this case, we found that the first damped fundamental mode was actually at 8.698 Hertz. Now, in order to calculate damping, we will have to convert the frequency spectrum curve in figure A into the figure D. And this, I'm sorry, figure B into figure D. In figure B here, the spectrum curve actually has multiple modes with all the modes that we measure from the free vibration. And In order to get the clean single mode response, we use a double Gaussian filter to remove all other modes. With only the first mode present, then you convert this modal curve back into the time domain. And that's how we have the result on the right of the slide. And why do we need this curve? Because we want to use attenuation curve to calculate the damping coefficient. The first thing you will calculate is the damping mass ratio, or C/M. And another reason for using this kind of time domain technique, as opposed to use other frequency domain techniques to determine damping, is because if you have the time domain curves here, we actually have two sets of boundary conditions. You have the positive peaks and also the negative peaks. By curve fitting, we found that the positive peaks and the negative peaks curves showed a very close agreement, giving us the confidence that the damping mass ratio that we obtained from this calculation was correct. In this case, we found that the damping mass ratio was 1.4551. Now, once we have the damping mass ratio, the next thing we can calculate is to calculate the stiffness mass ratio. So far, all we have is just ratios. We have damping to mass ratio, stiffness to mass ratio. And this stiffness to mass ratio can be directly calculated from the fundamental frequency. So what should we do next? The next thing we should do is to calculate the absolute value for the stiffness. Because once we have the value for the stiffness, you can calculate mass from the stiffness mass ratio. And if you have the mass, then you can use mass to calculate damping from the damping mass ratio. So this is essentially our approach. But there's one problem. The problem is, when we collect the data from this bridge, we have no information about the dead loads, meaning that we do not know how heavy those locomotives were. Neither do we know how heavy or the distribution of the loads of those passenger trains, because MBTA does not keep an information on how many passengers was in those passenger trains. Furthermore, we have no way to control the passengers to stay at the fixed location. So it is possible that the passenger could actually walk and sitting at different seats. That's why we propose an approach to address those uncertainties. And this is what we call the bounding approach. So what's the bounding approach here? In the bounding approach, we assume that the locomotives were full weight. This, of course, was not true. But by assuming that this locomotives were full tank, that is the heaviest weight ever possible for the locomotives, we will get the lower bound values. For the passenger trains, we assume that they're empty. Of course, that's also not true. But by assuming that the empty passenger trains, you will give us upper bound values from this calculation. So the full tank locomotive weight we found was the 282 kips, and the passenger train, the empty car weight was 106 kips. So let's get on to the stiffness calculation. This is essentially a structural analysis problem, but it's a dynamic one. What we need to take into account here is to know that at the location of, for instance, the first peak, this was the first axial load at the midspan of the bridge. But this load was not caused by only the first axial load. It was actually caused by the combination of whatever the axial loads were on the bridge. And that was a dynamic situation because along with the moving of the locomotives, this load combination actually changes. What is showing here is that in the picture B here, when the first axial load was at the midspan, there was only the locomotive on this bridge, meaning that the bridge still had not filled the weight of the first passenger train. But with the moving of the locomotives to, for example, the third or the fourth axial loads of the locomotive, the passenger train's axial load starts participating in the force response. And that's what we meant by this calculation has to be done in the dynamic scenario because the load combination are changing over time. With the same idea, to determine the upper bound values, you will have to consider the different loading scenarios. For instance, in here, the first peak load from the locomotives, we choose the third axial load because the third and the fourth axial loads of the first passenger train was actually close to the first two axial loads of the second passenger train. And this is reflected in our dynamic response. We are essentially leveraging the peak response to calculate the load combinations. And we can repeat the same scenario for the other three peaks in order to have the statistical understanding about the load distribution. Similarly, in this case, you can see that there are 4 different load combinations representing individual load response in the displacement curves. Now, once we have this response and curves, what we have to do is to run the optimization. And this optimization is basically based on the unknown weight distribution coefficients, because we did not know the distribution of the weights for among the axials. So in the upper bound calculation, there are 4 axial weights per passenger train. That means there are 4 weight distribution coefficients. For the locomotives, the problem gets a little bit complicated because you have to consider there are 2 other axial loads coming from the passenger trains. A locomotive has, in this case, has a 6 axial loads. But in the response that we have, you have to consider the first 2 axial loads from the passenger car. And the optimization gives us the final result, which is shown here. That means that for the passenger train, the majority of the load was actually in the second part of the passenger train. For the locomotive, the similar findings were found in this result. So instead of finding a single value in any kind of damage detection system, we actually found that a range, which is the upper bound value and the lower bound value. So after calculating the stiffness, we found we use it to determine the mass and use it to calculate the damping. Therefore, this result tells us that the range or the width between the upper bound value and the lower bound value was only 4.485% of the lower bound value. And this gives us a great confidence in believing that this approach actually can help us to monitor the degradation of the structure. What we expect in the future is that in the future, this range may shift over time and to indicate the change of the structural condition of a real structure. Now, let's talk about the second techniques, which is distributed optical sensing. I'm gonna let my colleague, Professor Xingwei Wang, to talk about this first.
Thank you, Tzuyang. So this sensing textile is very interesting technology. The advantage is that it can embed, for example, the optical fiber distributed sensors into this textile. The advantage is that it can have multiple parameter measurement at the same time, and also can apply in a large area structures, for example, the bridge here. So in this slide, you can see the pictures of this sensing textile. We can design different kinds of pattern based on the requirements. And thanks to Xingwei, who actually help us to do this manufacturing. So this video shows that they are embedding these fiber sensors in textile in real time. Next slide, please. Now. Thank you. So in this sensing textile, we can embed different kinds of sensors. So including BOTDR or BOTDA, which actually can measure a long distance up to, let's say, 80 kilometers or even 100 kilometers long distance with 1 meter spatial resolution sensing. Or OFDR, which have 30 or 50 meter long measurement, but with sub-millimeter spatial resolution, very high resolution measurement. It can be include the FPG sensors, which can have hundreds or even 1,000 sensing points in the fiber, and also could be the DTS sensor, which are very good for the dynamic measurements. Next slide, please. Here is just a very brief introduction how this works. So we all know that when the light travels in the fiber, it will have some scattering. And the well-known scattering is the middle one here in the Rayleigh scattering. And based on that, people developed the OFDR sensor. And if based on the Brilliant scattering, people develop the BOTDR or BOTDA measurement, can measure both strain and temperature. And for the based on the Raman scattering, we can develop this DTS sensor, mainly focus on the temperature measurement. And all these are fully distributed sensing capability, which means that along the fiber, you have many points of the sensing measurements. Next slide, please. And here we actually are very lucky to have the opportunity to conduct a few tests in Maine, collaborate with Maine DOT, AIT Bridge, and UMaine. And the sensing textiles were installed and tested in FRP composite bridge in Hampden, Maine. Next slide, please. And so back in 2020, actually our team is UMass Lowell and also UMaine together. We actually installed this sensing textile. You can see the students unrolling the sensing textile inside this girder before the girder were built into the bridge. And then after 1 month, we also go back to do the measurement on the baseline. Next slide, please. And then after you can see that the bridge was built using these girders, we do another measurement on the baseline and then conduct this vehicle loading test. Next slide, please. And then 1 year later in 2021, we went back to do another test with the traffic on the right and also without the traffic on the left. You can see the pictures. Next slide, please. And then here are some results. So as we said, for this test, we use the BOTDR, and BOTDR and BOTDA can measure both the strain and temperature at the same time. And these results actually show the strain distribution, and the x-axis is the distance. And the light blue one actually here and zoom in the bottom figure shows the strain distribution where the sensing textile were installed inside this girder on the bridge. And you can see that from October to November, so after the installation, 1 month, so we can see there's some shift that could be caused by the epoxy during this drying, and also the you can see there are some locations marked here mentioned showing that the epoxy finished uneven distribution during the installation. So although we try to use the roller to even out this epoxy, but there are some points that still because there's manual installation, so there are some points there, but the sensor can find out where are those locations. Next slide, please. And this slide, you can see that through this sensing textile, so from 24 to 40, about 45 meter, which is where the sensing textile inside the bridge, this whole distribution of this strain distribution. And this experiment results actually agree pretty well with what Professor Yu's group's model experiment results, the model analysis, and he will talk about that in the following slides.
Thank you, Xingwei. The problem for health monitoring or system identification at hand is a very challenging and interesting one. It's because from these measurements, we have to consider the unknowns at the support rigidity as well as the unknown values for the EI. Even so, they are design values from the manufacturer, in this case, the AIT bridges. But when we fit the distributed strain measurements with our simplified bridge model, we have to consider that there could be over time that the ideal design condition was not the one as built. And this is actually reflecting in our measurements. So at the beginning, we use a double spring and simply supported uniformly distributed load system to calculate the dead load effects and use only the dead load effects to extract the flexural rigidity versus dead load ratio. So from our preliminary calculations, you can see that we fit after the curve fitting, we have 3 different values. And the mathematical form for the simplified model is also shown on this slide. After observing the changes of this, we notice that right after the construction, there's adjustments of the bridge to the support conditions. But compared with the data set a year later, we found that there's about 3.7% of reduction in the flux rigidity versus the dead load ratio. If we assume that the dead load did not change over time, that means this change must be due to the flux rigidity, which is a very important structural parameter for any bridges. And our plan in the future is actually to continuously monitor this bridge in order to reconstruct this condition index curve over time. Therefore, any kind of meaningful structural health monitoring effort must be at least in the long term, because our infrastructure systems do not age overnight. And they barely, for new construction, they barely age in the first few years, which is why health monitoring really demands an institutional effort to monitor the conditions, because the lifespan curve cannot be reconstructed unless there's an institutional effort to monitor the structures over the long period of time, such as 50 years or even 70 years. Now, in conclusion, we would like to share with you, from our field experimental data, we found that there are different options for the bridge health monitoring applications. If you use dynamic remote sensing, in this case, laser Doppler vibrometry, you can actually get the first modal mass, first modal stiffness, and the first modal damping with the approach that we presented here. And in reality, it is always difficult to actually measure the weight of the structures. Therefore, we believe that the bounding solution will be more meaningful and practical for the single value solutions, because the loading, unless you perform structural load test, you will never be able to know and have the weight distribution for sure. So we propose to use a bounding solution, meaning that by monitoring the change of the bound values and use them to indicate the degradation of structures. On the other hand, distributed optical sensing technologies use what we propose as sensing textiles, give us the confidence that sensing textiles can survive in severe weather conditions, such as the winter in New England. And we plan to continue going back to the bridge and collect annual data and gradually develop this condition index time information, such that we can use them to train our computer models to predict the future degradation of structures. And before we conclude this presentation, we'd like to take the opportunity to thank the funding agencies. First of all is the US DOT, TIDC. And as for my group, I'd like to thank my former doctoral students, Paul Tang, and master students, Jana Viniaka, and my current doctoral student, Mayan Zarsa. Xingwei.
Yeah, our group, I would like to thank my students, Ray Wu, Andres Biondi, Lidan Cao, Sabrina Abidon, and Guoqiang Cui. They have spent a lot of time in the field test and analyzed the data, and work closely with Professor Yu's group and our teams from UMaine. Thank you.
Mm-hmm. And we also like to thank our industry partners, Xingwei for helping us manufacturing sensing textiles, and our industry partners, CXX, for letting us to use the bridge to continuous data collection. And of course, also Lunatech Innovations for helping us to process the signals. With that, the disclaimer here is, of course, whatever we presented in this presentation do not reflect the views of the US DOT. With that, we would like to conclude the presentation and open for questions.
All right, thank you, Tzuyang and Xingwei. We are now going to open up the floor to the Q&A session. As a reminder, you can submit any questions you have using Zoom's Q&A feature, and I will be going through them from the top to the bottom. I'm going to open up the Q&A. I have one question for you, Tzuyang, and anyone else who wants to add anything. The first sensing technology example that you focused on used a steel railway bridge. Can this technique be applied to other types of bridges, say concrete or composites? And would the approach be as effective?
Mm-hmm. Yeah, that's a very good question, of course. majority of the bridges, for example, for highway bridges, they are either composite bridges, which is reinforced concrete pre-stress, and a small portion of it, like the signature bridges, are usually steel bridges. But in terms of the population, the majority is reinforced concrete bridges. So in theory, yes, we believe that the approach that we develop here should be applicable to any kind of bridges. The difference is the bridge models that we have to develop to feed the data. That has to be revised per bridge. For instance, the boundary conditions for steel bridges could be different from, and the age of these boundary conditions certainly will be different from the ones for reinforced concrete bridges. So it is the modeling part for the data interpretation that we believe has to be adapted to different bridge conditions. But the approach for the LDV, it should be essentially the same.
Great, thank you, Tzuyang. We had a question in the chat that Xingwei already answered through text, but just for everyone to hear the question, I'll just read it out. Is the crochet done by hand? Have you noticed an improvement in sensing capabilities from different knits, weaves, or crochet? And the answer was, it is manufactured by the machine, I believe at Saint-Gobain. The advantages are easy installation and customized pattern design. Did you have anything else you wanted to add, Xingwei?
Yeah, so for the sensing capability itself, I think depends on the sensors. But for textile, actually the advantage they bring to is as I said, the easy installation. Because I think another question is related to that in the chat as well. Compare the sensing textile with the traditional strain sensing strain gauge. So strain gauge is the single sensing elements. But for the sensing textile, as we said, that we can embed the fully distributed optical fibers, which means that during one installation, you can have multiple sensing elements. For example, in the bridge or in the pipeline, this is very long or very large infrastructure. After in one installation, you can collect many sensing points at the same time, so which could save the installation time, and also can have multiple parameter if you want, for example, temperature and strain at the same time, do this measurement in the real time. So I think those are major benefits of the sensing textile.
Great, thank you, Xingwei.
Aaron, sorry to interrupt. I just realized
Yes.
that since we have Mr. Elvis Higgins here, maybe Elvis can chime in the bridge types in railroad industry.
Absolutely.
You name it, we have it. We have everything from heavy timber bridges that were originally constructed in the early 1900s to brand new concrete, metal, cast concrete, metal. There's about 10,000, or excuse me, about 9,000 bridges on the CSX system. And we're a 200-year-old organization, and so we run the gamut. If you can think it, we probably have it on percent.
Perfect, thank you both. Related to the last, did you collect data from one location at a time? How did you deal with non-synchronous data processing?
Was the question about the LDV or for the sensing textile? I think it's for the LDV, right?
I believe so as well.
Okay. Well, for the LDV, this was, if I can share my slides. If you look at the duration of our data here, it was only about the raw data. It was only about like 120 seconds. So that's very short. And this was actually in one measurement. So that means this is a single point LDV. We only look at the mid-band vibration. As opposed to, there's another technique called scanning a laser Doppler vibrometer. SLDV scans the entire bridge, which collects the dynamic response at different locations. Despite that, it's more powerful than the LDV, but the cost is, of course, increases if you use the scanning laser Doppler vibrometer. I hope I answered the question.
All right, I think so. And more in depth here, how will the data be used to assess the bridge condition or recommended maintenance or replacement?
Mm-hmm. And our answer to that is we propose to use the variation of, or say the shifting of these bound values to indicate the degradation of the bridge. Now, in principle, the degradation of bridge is usually associated with the decrease of stiffness. In this case, we measure the modal stiffness for the first mode. And the damping, it depends on the boundary conditions and how the bridge was designed. In reinforced concrete bridges, usually the increase of damping is associated with the increase of degradation or defects. So that's for reinforced concrete structures. But for railway infrastructures, for example, the monitoring of the railways, the railway ballast, the damping for the railway ballast actually decreases with the aging of the infrastructure. So there are so many different types of civil infrastructure systems. But I believe that that's the physical knowledge that we need to develop for a particular type of structure. And with that, then we can use it to advise the stakeholders whether there should be actions taken because of the stiffness has dropped below certain values. Now, what we have here is just the snapshot of this bridge at this time. Eventually, what we need to have is the time-dependent curve, which is something look like this. So we plan to use those mechanical properties as the condition index for health monitoring.
Perfect. And we have a bit of a clarification from one of our earlier questions. The question before was, did you collect data from one location at a time? And the clarification is, can this data be used to calibrate an FE model using model analysis?
Mm-hmm. Yes, absolutely. What we did not do in this case study was we didn't build the finite element models, or we didn't have any kind of digital twins. The goal was to be able to use to explore that if the measurement could only be done in a very short period of time, and with that information, how much can we learn from that loading curve? In this case, it was only about 120. It's about 4 minutes data. How can we learn from this 4 minutes dynamic measurement data at the midspan of the bridge? So that's the measurement constraint that we created for this particular case study. But we certainly, this result can be integrated or compared with a finite model and to create a digital twin for the bridge. I wonder if this would be something of interest to the rail industry, but for state DOTs, I think it's only done on the case-by-case basis.
Great. And before we move on to the next, does anyone have anything to add to that question there? Okay. Well, one more question we have in the chat currently is, have you developed any lessons learned or best practices for long-term adhesion to the textile sensing fabric to the surfaces? I think that's a good one for Xingwei.
Yeah, sure. We have both our team and I think Tzuyang's team. We learn together. We have a lot of good lessons. So first of all, the surface. So this also depends on what kind of surface. So the surface needs to be very clean before we actually embed this textile. So actually we have conducted this field test in both this bridge on this main on the girder and also the New Hampshire bridge Professor you just mentioned. So for both of them, actually we first need to clean up this the surface, And also when we unroll this sensing textile and put this epoxy onto it, need to roll this evenly and very carefully, do not have any air bubbles, and on aggregate of the epoxy onto the surface. That's very important. For the New Hampshire bridge, actually, because that's the existing bridge, so actually the installation was conducted by the company, and they actually need to clean up the surface to because existing bridge, they already have a lot of the dust and also some existing debris, things like that. We need to clean this out very, very carefully and clean before we install this textile. For this main bridge one, because it's a new structure and actually was installed by our students, and they try to do a careful work, but still you can see from the results there's still some air bubbles. As we said, that should be really be very careful during this installation. Tzuyang, you want to add something?
Yes, I could add some information, some background information. The type of epoxy we use, it was a commercial one. I believe the company is called Western Systems. It's a 2-component epoxy. So the first component is 105, and the second, the mix integrator is the synergizer is the 205. So the reason we choose that particular epoxy was because it was adequate for concrete and composite separately. But we didn't actually, there was no case study to show that if we bound textiles to composite surface. However, from this case study, we think that if you choose the epoxy specifically for concrete or for composite, that should work very well.
Great. So I have a question. It's kind of an open question to anyone who has an answer. What are the next steps, either in these two technologies or in bridge sensing in general? This is a great step in the right direction. Do we see widespread use of these technologies next? Do we see a further advancement of these technologies next? What are the next steps?
Well, I can take the question from the researcher's perspective, but we also have end users, Elvis here. He may have something else in mind. As a researcher, we certainly like to create higher, better technologies by using the higher resolution, but consequently, the costs will increase as well. But I think the efficiency will always be there, because if the measurement takes too long to collect the data, then it will increase the cost as well. So I hope that in the future, we could actually design structures by considering the needs for inspection or for monitoring. Today, there's no such idea in the design, from the design stage. But for future bridge constructions, I hope that this can be part of our paradigm.
And I would say that eventually, we would like to not put people in harm's way to inspect a bridge and use remote sensing technology. Right now to inspect a bridge, we either have someone, climbing along the bridge wearing fall protection or working from a boom truck. And so, if we can get the same, level of inspection and level of risk detection, without having to put that person there, and then send that person, once the system detects something, that experienced bridge inspector put his eyes on the issue and verify. I think that's what we would like to get to mention.
And I think too, there's an aspect when you look at from the inspection based off of, Elvis's statement, as we move to these FRP composite structures, inspection is different now. It's different from a concrete reinforced or steel bridge. So the techniques being developed by Xingwei are, going to be critical for inspecting some of these bridges as composites take more of a place in bridge design and bridge deployment.
Right. And speaking of FRP bridges, are there any are there any approaches that are tailored specific to FRP? We're speaking about FRP bridges as the next step in bridge development. Is there any thoughts towards sensing techniques that are specific to that kind of technology?
Well, from my understanding, this actually is happening in the aerospace industry. They have composite FRP brick aircrafts, so they already have embedded sensors in there. But FRP has been used in civil engineering for retrofitting and strengthening back in the 90s, especially in California, and to repair and retrofit those seismically damaged bridge piers or girders. They use FRP sheets or layers to wrap those concrete components in order to provide enhanced confinement to improve the bearing capacity. So that has been done. But from this collaboration, what our UMaine collaborators were trying to do, and also the industry like AIT bridges, is to replace concrete and steel completely with composite. And like Matthew also pointed out, that this will require a very different understanding on the aging as well as the monitoring scenarios, because it's a different material and it has different structural behaviors.
Right. And with the anti-corrosive and longer lasting nature of FRP, I imagine that kind of changes how you take a look at sensing, how often you record this data, just a whole new approach from steel and concrete to FRP.
Mm-hmm.
And if you go one step further, look at it, if your bridge has an accident on it, how do you inspect the bridge if there is a car fire? Some materials will hold up much better. Or if there's something, like that type of an event, a thermal event, there needs to be a good way to ensure the structural integrity of that bridge.
Mm-hmm.
Absolutely. Well, it looks like no more questions are coming into the Q&A chat, and we're getting right about to the end of our time. So I guess we'll go around and do any last words from anyone, anything to leave the audience with for today.
Okay. So I would say that because they are civil infrastructure systems are a very diverse group of structure systems, and of course different materials. So when it comes to sensing and inspection, they are only sensitive to certain types of, for example, perturbances. And that is why, as an inspection researcher in civil engineering, he or she will need to learn more about materials behavior, structures behavior, and as well as the pros and cons with different sensing technologies. Here, we only presented two combinations: laser on the steel bridge, sensing textiles, or optical fiber sensors on composite. But out there are tons of combinations of different sensors and different structures. What is the best solution? I think that's still a research question yet to be found for future generations.
Thank you, Tzuyang. Xingwei, any last words?
Yeah, I appreciate this opportunity, and I think we are continue to open to the collaboration between the academic and industry, and to work together to solve all these existing and also maybe the new coming problems. So I also want to take this opportunity to thank UMaine and also our industry panels. Thank you very much.
Awesome. Thank you, Xingwei. Well, thank you all for joining us for the TIDC June webinar on dynamic remote sensing and optical distributed sensing applications for bridge health monitoring. I want to thank both you, Tzuyang and Xingwei, for presenting, and also Elvis and Matthew for being on our panel. You all provided some great information for our audience today. I'm going to share a couple more slides before we officially end for today. We have another webinar coming up this October on another TIDC research initiative, guidelines for span and skew angle ranges on integral abutment bridges, by by TIDC researcher Dr. Susan Faraji. And we're going to have a collaboration with Vermont Agency of Transportation. They have some bridges that we'll be talking about in October. In August, we will be having our TIDC annual conference as well. Join us this August 6th through 8th for the TIDC annual conference, where we'll have 3 days of diverse transportation related topics. I'm going to be placing a link in the chat for you to learn more. And lastly, if there are any questions that we weren't able to address today, if you think of anything else that you want to ask any of our panelists, I encourage you to scan the QR code or follow the link on screen that will bring you to TIDC's Contact Us page. There's an option to select webinar follow-up. This will prompt you to enter a few pieces of information so we can get back to you with your questions. And lastly, the recording for this webinar and a certificate of attendance will be available at the link in the Zoom chat now.